tell us that any function, not only the functions that we have been more frequently accustomed with, but even functions that are of higher order, that is functions which take functions as input, can return functions as output, everything can be expressed in lambda calculus. We have seen basic some simple lambda expressions. We have seen how Boolean algebra can be represented in terms of lambda expressions, how numerics can be represented, and most importantly, what we discussed last Monday was how using Y Combinator we can actually express recursion in terms of lambda expression. How we can also handle functions of multiple variables, either by pairing or by currying, and the whole higher order function behaviors. So this was to provide the syntax for the lambda expressions. Now, we will move on today to discussing the semantics of lambda expression. I hope this is visible, right?
Yes, sir.
Okay. So we are moving into module 3, which where we would discuss the semantics of lambda calculus. Now, before I get into the process of developing semantics, let us ask ourselves as to what is semantics. So we say semantics is a meaning of an expression. So if we write x assigned y plus 2, then the semantics is you take the value of y, add 2 to that, and assign it to the variable x, and so on. So semantics is also if x and y are objects of certain class, and plus is an operator in that class, and there is a default then there is a constructor which can take a integer constant and construct an object, then the semantics of x assigned y plus 2 could be very different from adding numeral 2 to y and assigning it to x, right? So the question is, when we talk about semantics, we say that it is meaning of an expression. Now, what is the meaning of meaning? I mean, what do we mean by saying this is the semantics or this is the meaning? This brings us to a little bit of a circular logic, little bit of a philosophical question, that we are writing an expression in a certain language, whether it is C, it is C++, it is Java, Python, or lambda calculus. We are writing different expressions. And then we say, what is the meaning of that expression? What is the semantics of that expression? Now, if I have to say what is the semantics of that expression, I need another language. So assuming that I have control over a language which I understand, so that given the expression of a language, whether it is C or lambda calculus, I would express that in the language that I know, and that will make me understand what that expression means, what is the semantics of that expression. In other words, semantics always need a vehicular language, a language which is already known, a language in which expressions or constructs or operations have very clear meaning. So often understanding semantics becomes a process of transformation from the expression of the given language to an expression in the language, vehicular language that I know. Think about C. In C, we write a program and we compile. What do we compile into? We compile into the assembly language of the processor on which we want to execute it. Now, obviously, the first part of that is checking for syntax. So we make sure that syntactically it is a correct expression, which is simpler part. Then we say that this is what it means. I say X is assigned 5, Y is post incremented, and so on, has a semantics. What is that semantics? That semantics is the equivalent assembly code that represents this particular expression. So it's a transformational game. Semantics is a transformational game. So if my vehicular language change, naturally I'll have to interpret it in a different way. Otherwise, what do we do? We'll say, no, that is not the book by Carnegie and Ritchie explains the meaning of every expression. Well, what is a vehicular language in that case? The vehicular language in that case is my natural language. When I say X is assigned 5, we are saying 5 is a constant, X has a memory location, X assigned 5 will make sure that the representation of 5 is put in that memory location so that henceforth, whenever I use X, I will get that value 5. I say that in English. I can say that in any other natural language also. But again, to express the semantics, I'm using a vehicular language. Now, using a natural language for expressing semantics is full of ambiguity. What I say and what you understand, what you say and what I understand can always be, there can always be gap, and you have seen several occurrences of such gap in terms of the programming languages that you have seen. Using an assembly instruction or assembly language as a vehicular for semantics is better because assembly has very low level primitives and very limited way that you can interpret them, fine. But the whole transformational process itself is kind of ad hoc. So you have seen this when you have written compilers. In writing compilers, you have written whole lot of rules. Again, using, say, the C language or C++ language to express the meaning of a given C++ expression. Now, that ad hoc set of rules are the transformational method of expressing the semantics of C++ in terms of some other assembly language or some other intermediate representation language and so on. Right. So there is always a scope for interpreting the same expression in 2 different ways, 3 different ways, interpreting it wrongly, and so on and so forth. None of these are kind of mathematically sound, solid mechanisms. So in terms of semantics, we come across 2 core issues. First issue is, what is my vehicular language? In what language shall I express the semantics? Because then the semantics of that language will again have to be expressed in some other language. The process does not end. So the choice of the vehicular language is very important. And the second is, what is my transformational mechanism by which I transform the given expression into an equivalent expression in the vehicular language so that both of them have the same semantics as I have intended. And so far, whatever examples you have seen, you have in terms of compiler studies, you have seen several examples. You would have seen that the vehicular language could be of various different forms. It could be the 3 address code. it could be the assembly language, it could be other representations. And the transformational mechanism is ad hoc. Is some human understanding by which you do that. And then simply you keep on doing a lot of tests to ensure that the semantics is correct. So this is the current understanding of expressing semantics. We will deviate or kind of get foundational in terms of defining the semantics of lambda calculus. And that exception or that special case is in terms of answering these two questions. One, what is the vehicular language of representing the semantics of lambda calculus expressions? It is lambda calculus expressions themselves, which is something very, very interesting, that the whole meaning of meaning is being given differently now. You don't use a third language. You don't use a second language for the vehicular, but you use the lambda expressions themselves as a meaning, as a semantic. So we'll have to define what does that semantics mean. But the choice of the vehicular language is within lambda calculus itself. So you free yourself from the dependence of another language and the circular question of what is the semantics of different expression in that language. Second part, the transformational process, we will define a set of mathematical rules, logical rules, so that those can be applied even in an automated manner or by a human being, but they are strict rules so that there is no scope for separate interpretation. So from the given lambda calculus expression, we will apply these transformational rules and keep on applying them till we reach a certain point where we have a transformed lambda calculus expression, which we say is the semantics of the original expression. So that process of transformation of the original lambda expression in terms of what it semantically means, that equivalent lambda expression, that process of transformation is called reduction. And for this, we have a set of mathematical rules of reduction: alpha, beta, eta, and delta. And that ensures that it is not like in a compiler, the particularly very, I mean, some questions are always very open. Yes, please. Okay, please mute yourself. For example, you do plus plus a, pre-increment. Now you write plus plus a plus 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 a. Now the semantics of this is often quite open to interpretation. The question is when will the actual pre-increment happen? Will it happen before the additions or after the additions? Okay, you say, okay, it is pre-increment, so it will happen before the addition. Fine. Think about now a plus 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 a plus plus. So it is post-increment. The question is, will the original value of a will be used to add with a, and then it will be post-incremented twice? Will the original value of a will be added to original the same value, but it will be post-incremented once? Or will the value of a in the first place will be post-incremented, added to the original value, and then a will be incremented again? There could be different interpretations. It is post-increment will happen after. That after has a lot of ambiguity, and therefore you'll see that if you try to evaluate these kind of expressions, complex expressions in different compilers, potentially you get different results, because your transformational process itself is not mathematically sound. So Lambda calculus, as I said, is a vehicle of providing a solid foundation for programming languages. So it cannot let this kind of open interpretations, humanly open interpretations, to affect the whole process. And therefore, the whole transformational process is a set of strict mathematical rules, and there is justification for why these rules are. It's not just magic. And the target vehicular language into which the lambda calculus expressions will be semantically expressed are lambda expressions themselves. So that is the background expectation that I'm trying to set. So with this words, let us quickly get into seeing what this is. So much of the content in these slides are taken from this source. This link is, there is a link here actually. You can go there and get more details. So I start again by quickly revisiting the concept of free and bound variable. We have talked that an occurrence of a variable is said to be bound when it occurs in the body of M. If I have lambda x dot M, then all occurrences of x in M is is bound. So this lambda x is called the binder, and M is the scope of binding, which is, this is obvious. An occurrence of x is free if it appears in a position where it is not bound by any enclosing binder or any enclosing abstraction on x. So very obviously, x happening in xy is free. X happening in lambda y dot xy is also free, whereas y here is bound. Occurrence of x in lambda x dot x is bound. Occurrence of x in this expression is bound. This x is bound by this binder. If I have lambda x dot x within parenthesis x, then the first occurrence of x is bound, whereas the second occurrence of x is free because there is no binder on the second occurrence of x. Right. So that's the concept of free and bound. We have seen it in the syntax. I just did a quick recap. So in a loose parallel to C functions, we can consider that bound variables are those which are local to a function, including parameters, and free variables that are those which are non-local. So in an abstraction, the variable named is referred to bound variable, and the lambda expression is called the body of that abstraction. So here, these examples also we have seen. Okay. So I just want to give you a pointer that this whole concept of free and bound, this whole concept of free and bound are not necessarily new to us. We have used it in several contexts earlier, maybe not specifically giving it this name, but a different kind of in in integral calculus, we have indefinite integral and definite integral. When we have a definite integral, then naturally this dx is a binder and x is a bound variable, and that binder applies to these limits. Whereas if I write a star x squared dx, then x is bound, but a is free. So because it can take any value, but x cannot. X is bound by dx. Similarly, in a discrete form, here x is bound, here x is bound, but k is free. Here in the limit, x is bound, this is a binder, and m is free. In function, of course, in terms of quantification in logic, when you say for all x r, then x is bound by this. If I have some other variable on which I do not have a quantifier, then it is free. So it is different domains do use the same concept, but according to the domain, we have either have a different name or we do not have a name. We just have a implicit understanding, but the concept is very similar. So an occurrence of a variable v in a lambda expression is called bound if it is within the scope of a lambda v, otherwise it's called free. Good. So the first mathematical process or algorithmic process that we do is to, given an expression, I want to find the set of free variables. So if E is an expression, I say FV, free variable E, is a set of variables occurring in E which are free. So kind of there is a recursive definition for the same. So if E is a constant, of course, there is no free variable. There's no variable itself. So this is a null set. If it is any variable, if E is any variable, then the free variable in E is that variable itself. If I have an application of E1 on E2, the free variable of that application is a free variable of E1 union free variable of E2. Very simple. If I have an abstraction, then I have a binder on X. So the free variable of the abstraction is a free variables of E, but X occurring in E is not free anymore. So you take out X. Ignore the second minus. That's a typo. This is just a set difference. You take the free variables in E and take out X. So this is a simple recursive definition which, given any lambda expression, can get you the set of free variables, because that will be very critical for the process that we are going to define in terms of getting the semantics. And when a lambda expression has no free variable, then it is called closed. So it's a closed expression. So as I said, so what we are trying to do is we are trying to define a transformational process. In the transformational process, which is called substitution, or which is substitution rather, it will be formally called reduction once we have defined the rules. Our target would be to take a variable V and a lambda expression E and substitute this variable V by another lambda expression E1 in E. So E is a lambda expression. Just take a good note of the notation. This notation is heavily used henceforth. V is a variable necessarily. E and E1 are two lambda expressions. And this notation means a substitution, substituting all free occurrences of V in E by the expression E1. Right? This is what I define as a substitution. Obviously, this is kind of an unambiguous definition and can be kind of rolled out as a set of rules. Right? So that's what I try to do. So again, let me and in every case, I should have also highlighted in case of free variable that the recursive definitions in all these cases or all these rules follow the basic structure of the lambda expression, which is either a constant or a variable or an application or an abstraction. So these are the basic rules to form the lambda expression syntactically. So any lambda expression is built out of this. So for each one of these builder, if I can define the corresponding rule, then I'll have a rule for every expression. So that's the basic thought process. So if I have a variable, if my lambda expression E is a variable V itself, then what will be the substitution? You are substituting V by E1 in V. So what will you get? You will get E1 naturally. Now, if you students just wait for a minute. There is someone at the door. I will just answer the door call and come. Just 2 minutes. Hello, I'm back. Sorry about that. Hello. I'm audible again, right?
Yes,
Yes.
sir.
Okay. So, in terms of substitution, we try to see what will happen. So, if I have a variable in the expression, naturally the rule for constant is not meaningful, because if there is a constant, then there is nothing to substitute. So if E is a constant, then there is no substitution. Obviously, it has no effect. But if E is a variable and if E is V, then substituting V by E1 in E is E1 itself. Very simple. If it is a variable which is not V, some other variable, then naturally there is no occurrence of V itself in E. So there is nothing to substitute. So it remains X. Simple. Now, so
So what do you mean by free range of
pardon? Pardon? Could you repeat the question, please?
variable? What do you mean by free occurrence of variable?
We just defined what are
Is
the
it
free
like
variables. Well,
okay, the free
so again, E could be something like, I'm just going back. Say E could be something like lambda y dot xy. Right. In this, X is free, Y is not free. So X I can substitute by some other lambda expression by substitution, but Y I cannot, because Y is not free. Right. So X has a free occurrence, Y does not have a free occurrence. Right. So you'll have to little bit keep on thinking and practicing, because this concept of free is very important. So something that can change, that's basically what it is saying. So these are the exit rules for the recursive definition. Then we have the abstraction. If I have lambda v dot e, v is substituted by e1, then it is lambda v dot. So I'm doing a substitution, so that substitution will apply to E. So E is in E, you replace V by E1. Simple. If I have an application, E retter, E rand, and I'm doing a substitution of V by E1, then it is substituting V by E1 in the retter, substituting V by E1 in the rand, and then doing the application. Right? So this is kind of, I mean, mind you, I'm saying these are naive rules. So this is kind of the first thought that we will have is, if I have to do a substitution, then I will start with the primitives, which are variables, which are rules A and B. And then for the two builders, application, abstraction, and application, I will extend the substitution rule. So I will, to apply to the substitution to the abstraction, I will apply the substitution to the body of the abstraction, and to apply the substitution to the application, I will apply the substitution to the function as well as the lambda expression on which that function operates, the retter and rand both, and then do the application, which is what we are trying to do here. Okay, let us try out. Let's see lambda y dot x, x substituted by, this is E1, lambda z dot zw. So we do the substitution. So we are applying rule C. So we will have lambda y dot x is being substituted by this E1. So in place of x, you write this E1, which is right. So it seems like that our rules are starting to work. Okay. Now let us consider lambda x dot x is E, E1 is y, and I replace x by y. This is a substitution. So by our rule, again, rule C here, this rule C here, I will do the substitution in the body. So it's lambda x dot x substituted by y. So this becomes lambda x dot y. Well, if you have done that, then what you get is a different lambda expression. The original lambda expression was identity, like lambda x dot x. And our intuition is that no matter what the variable is named, if I rename the parameters, it will remain the same function. So lambda x identity function could be lambda x dot x or lambda z dot z or lambda ppd dot ppd and so on. But this substitution rule that we have created does not work in that way. So what is the mistake that we are making? The mistake that we are making, I highlight in red, is that the substitution should apply only to free variables and not bound ones. Let us go back. What did we say? The notation refers to the lambda expression obtained by replacing each free occurrence of the variable v in E. So this replacement should occur only when x is free in this expression. This is expression E. If x is free in this, then this substitution should take place. Otherwise, it should not. But we have not, when we applied it here, or going back, when we have built this rule, we have not put that consideration. We have just, okay, if you have to do the substitution in the abstraction, just go and do the substitution in the body of the abstraction. But that is why we are going wrong, because that is what means that I did not check so that may not work, as it is not working here. So if we remind ourselves that the variable needs to be free and then try to build the rule, then we will see that for the substitution in the identity lambda x dot x for x replaced by y, the result should be lambda x dot x because x is bound, so there is nothing to replace. Right? So these kind of substitutions which change the original lambda expression or whatever the original lambda expression stood for are known as unsafe substitution. So our rules are not sound because they are allowing unsafe substitution. Let us take another example of unsafe substitution. So what we learn from here, we are trying to kind of put it in our mind very strongly that for substitution, the variable we are substituting for must be free in the expression where the substitution is taking place. Bound variables are not possible. The lack of safety can happen in a different way also. Again, let us try that naive substitution. Here the expression is lambda x dot mul x yx. Right? And we are doing a substitution of y by x. So what we will do? According to our earlier learning, we check whether y is bound in this expression. We see no, y is not bound, x is bound, but y is free. So we go ahead and say, okay, this substitution can be done, and we do the substitution. We substitute y by x, and this is what we'll get. But now if you compare the original expression and the expression resulting from the substitution, they are different expression. The first one multiplies x, any x, with a given y, whereas the resulting expression after substitution is basically a squaring function. So we are again, our rule is going wrong even after we have taken care that the variable that we substitute for is free. What did it go wrong? It went wrong in the place that what is really happened is when I substituted y by x, this x gets bound in the substituted expression. So a substitution is valid or safe if no free variable in U1, it was free here. In U1, it was free. If no free variable in U1 becomes bound, it has become bound as a result of this substitution. So x was free, and because of this substitution, after substitution, it has become bound. So that is giving us unsafe substitution. This involves what is called a variable capture or a name clash, because you are basically this x, this free x, and this bound x are having different names. So what could be the correct way? The correct way could be that, well, and if any variable is bound, then I can actually rename it to something else. So let me rename it in the original expression to some other which is different from x. So this was my original substitution. I transform it into, by this bound x, I transform it as z. I rename it as z. If I rename it as z, then I get this, which is again repeated here. And now I do the substitution. Now I satisfy both the observations. One, the variable I'm substituting for is not bound in this expression. And after substitution, the variable x, which was free, will not get bound in the substituted expression. I replace y for x, x for y. I get this, which is not got bound. It was free, it remains free. And now if you compare the original expression and this substituted expression, it is just some kind of a certain renaming as if has happened, but they are actually the same expression, same lambda expression that we have. So we have the equivalence between them. It is a safe substitution. So we have observed, going back again, we have observed this rule of ours, the rule of substitution in the application, needs to have more consideration to ensure that the variable I'm substituting for, v, is not bound in the expression. And second, no free variable in the expression that I have substituted should become bound after the application of the substitution. Right? So these are these two counter examples. This is the basic learning that we have taken. So we now redefine the substitution rules. Again, the same target. The substitution of an expression for a free variable in a lambda expression is denoted by this. And this is our definition. Now we are giving a complete definition. One is, the first rule remains the same. If the expression is v, then replacing v by e1 will give you e1. No conflict, because certainly v is free here. So this will work. If the variable is, if it is a variable x other than v, x is not equal to v, then doing this substitution has no effect. You'll have x. If it is a constant c, then of course there's no effect. It remains a constant. If it is an application, then we do recursively the substitution in the retur and the rand, and then do the application. That is fine. But in coming to the abstraction, we now have to put to consideration the observations that we have made. So if lambda v dot e is my target to be substituted, where v should be replaced, substituted by e1, then we will not be able to substitute anything because v is bound in this expression. V is not free. So it will remain to be lambda v dot e. V is not free in e. Let's say now I have an expression lambda x dot e, and I'm trying to replace v by e1. And x is not equal to v, because then it comes to same as rule e. Now what I need that after the substitution, obviously after the substitution, whatever I'll get, in that x will become bound, because this whole expression is in the body of this binder. So I need that the substitution will work if E1 does not have a free occurrence of X. If it had, then we'll have that null issue, that a free occurrence will become a bound occurrence. So how do I say it here? I say that X does not belong to FV of E1. FV is free variables in E1. So this is just mathematically saying that X is not free in E1. So if X is not equal to V, and if X is not free in E1, then this substitution can be done. This is our rule number F. So there will be another condition to check, since I have put that X is not free in E1. So what if X is free? So I have the same expression and same target substitution. X is not equal to V, but X is free in E1. So how did we solve the null problem? We basically did a renaming of X in the bound scope. So this is renaming to some Z. What is renaming? Renaming is a substitution of X by Z. So on E, we first do a substitution of X by Z, and then we do the intended substitution, which is V by E1. Naturally, recursively now, again, all the rules of substitution of X by Z in E will apply. But necessarily what we are saying is you rename X to Z, which is not same as V, so that it does not clash, which must not be free in E or E1, because if it is, then eventually from free it will become bound. So you have to choose a variable Z, some other name, which make sure that these both rules are satisfied in the context that X is actually free in E1. This is the null example and the null workaround that we saw. So this rule G completes all possible cases that can happen in terms of the substitution in a Lambda application. Right. So now we have from 4, we have 7 rules. We have added the rule for constant, and we have for application. Now we have 3 cases when the variable itself is not free, when that variable is free, but there is some other variable which we need to check if it is free in the expression E1 you are substituting, and the third case is where you need the renaming. So now we have a complete set of substitution which converts one lambda expression into another without actually changing that expression. Right? So let us take an example. So just for reference, I have summarized, I have just referred the rules here. So this is what we intend to do. Lambda y dot, you have lambda f dot fx y. This is the expression E, and you want to replace x by fy. Right? So if I want to replace x by fy, then x will be replaced by fy. Right? If I do that, then what will happen? Y, which is a free variable in fy, will get bound because this y is bound, but y is free in E1. But if I do the replacement, then y will get bound. So I have to apply. So that is my rule G. So I apply rule G and do a renaming of y by z, applying rule G. So I get this. Now what do I have? I have this abstraction. So I will have to apply on this application where I have the rater. I do the substitution on the rater. I have the rand z. I do the substitution on the rand z. That is, I'm using rule D. I get this. Now, in this, z x is replaced by fy. So this is the case where I'm in rule B. That is, I'm trying to substitute x for in place of z, where x and z are different. So naturally, there is no effect for this substitution. So this substitution by rule B gives me just z, this rule B. Then I have to do this substitution. So I will substitute x by fy. Right? If I substitute x by fy, f is free in fy, but it is bound here. So if I do this substitution, the f will become bound after the substitution. Again, the case of rule G. So since f is free variable in fy, I need to do a renaming of f. So I rename f by G. These are, there would be intermediate steps I have not shown. So simply shown that replacement. So after that has been done, then I can do this substitution of x by fy. X by fy will have to be done in terms of applying it on G and applying it on x, which is rule D. Applying it on G will not make any change, rule B, it will remain G. And applying it on x will use rule A and make it fy. So this is the, I'm sorry, this is the resultant expression that we come to. So this is how the substitution does work, and these rules will ensure that your substitution is safe all the time. Let me stop here once and get back to you to see if it is at all. Any questions? Is it, are you being able to understand the process of substitution? I've explained the need for it because we are trying to create a transformation which will be mathematically sound. So we are just trying to do that. And we are yet to come to the point where we meet the first target, that the semantics of a lambda expression will be another lambda expression which is equivalent, the vehicular language requirement. But we have started off with this transformation process, which we are trying to make it sound and complete. So the completeness come from the fact that we have defined the substitution for every possible mechanism by which a lambda expression can be syntactically built. We have defined it for constant, we have defined it for variable, we have defined it for application, and we have defined it for abstraction. So these are the possibilities through which any lambda expression syntactically can be formed, as we have seen. So the completeness of the substitution rules are obvious. The soundness of the rules is what we have discussed, and by analyzing the counter examples, we have tried to build up finally into 7 substitution rules, which look to be sound to operate with. Okay. If there are no questions, let me again slowly proceed. I hope this is visible. So then let me start formally defining reduction. This is the meaning of meaning in lambda domain. A lambda expression has its meaning, the lambda expression that results after all its function applications are carried out. Right. So we are saying this is like saying it in this way, that let's say I have a factorial function. Right. We all know what it means, but what we are trying to say is that the meaning of factorial 5 is 120. The meaning of factorial 2 plus factorial 3 is 8. The meaning of factorial 3 times factorial 4 is 72, or whatever it comes to, 6 times 24. Okay. That value. So I say it's very simple. Lambda expressions are representation of functions. Functions are applied onto other lambda expressions. So if I actually do this application, then semantically there's no difference between factorial 5 and 120. So I can say the meaning of factorial 5 is 120. And we are doing that equivalent here. We're saying that we will keep on applying all functions that exist in the expression till there is no more left. We will use the safe substitution process to do this function application, so that at every stage, once we apply, one lambda expression gets transformed to safely into another equivalent lambda expression. And we continue this process till there is no more function applications left. And that is the meaning of the original lambda expression. It's little unconventional to think and absorb at the very beginning, but slowly it gets into the mind. So evaluating a lambda expression is thus called a reduction, and there are 4 rules of reduction. The first rule is alpha reduction, which is renaming, which you have already kind of seen. I will again formally define. Second rule is a core rule of defining semantics, which is the substitution rule, where you actually do the function applications. Eta reduction supports the process. It is called the function equality rule. That is, you say that if I'm given 2 functions, f and g, then when do I say, and of course, if f and g have the identical domain and codomain, say both from A to B, f is from A to B and g is also from A to B, when do I say that they are the same function? Very simply, if fa, the image of f, is same as ga, that is, under f, whatever parameter you take from A, it maps to some element in B. Under G also that happens. If all of these mappings are same, so that's what we say is the image. If FA is equal to GA, then we say that they are equal functions. So they may have been written in several different ways. Right? So we try to define function equality so that some forms can be even simpler. And finally, we have a delta reduction rule, which is applicable if you assume that you have predefined constants. So, for example, if you have a predefined constant function add and predefined constant 5, 3, then add 5, 3, this lambda expression can be reduced by delta reduction to 8. But if you do not have predefined constants, or if you are using certain functions and values which are not predefined, then certainly the delta rule. So delta rule is kind of simplifying, but the core of it is the beta reduction. And for doing that, as we have seen, the substitution can work. But in the in the substitution rule G that we have just saw, we saw a need for renaming, which is the alpha reduction. Right? So that's the whole gamut of stuff. So what is alpha reduction? If f and w are variables and e is a lambda expression, lambda v dot e, provided that w does not occur in e at all. W should not be occurring in e. This w should not be occurring in e. Then the substitution of v by w in e is obviously safe. You're just taking a new name. Just don't bother about checking what is free, what is not free, and all that. You are just taking a new name. So you say that W does not occur in E at all. If it is, then obviously I can replace V by W without affecting anything. So I take lambda V dot E. This I do the reduction, alpha reduction. This is the notation. The subscript alpha tells you that you are doing a renaming, and then it becomes lambda W. You have renamed V by W, and you do a substitution of V by W in E. And you have ensured that this is a safe substitution. Right? So what you have on 2 sides are basically equivalent lambda expression. The equivalence of expressions under alpha reduction is what makes part G of the definition of the substitution correct. So this is what we have thought. So it simply allows changing the bound variables as long as there is no capture of a free variable occurrence. And as you can see there on both sides, actually, if you have this expression, then you can also say that this is an equivalent expression. Right? So they are basically, as we say, are congruent lambda expressions. That is, if you think Am I audible or there's a connection problem?
Yes, sir. Now you are audible.
Yes, sir. Now it's
Yes,
audible.
there are connection problems at times. So the congruent lambda expressions are those which are equivalent to each other. Right. So in the last example that we did, we saw two alpha reductions. So in the first case, we changed y to z. So we have basically done this and got this expression. And in the second case, we changed f to g and got this expression. So we have already done this. So this is formally in terms of the alpha reduction mechanism. Next comes the beta reduction, which is actually the key of the semantics. It does the substitution. So if a variable, if v is a variable and e and e1 are lambda expressions, so you have lambda v dot e and on e1. So beta reduction will replace v by e1 in the expression e. So this is the meaning of the beta reduction, provided this substitution that you are doing is safe. We have already defined safety. So if this is safe, then this is the basic beta reduction, which as you can see is evaluating a function. So this beta reduction rule describes the function application rule in which the actual parameter or argument e1, this is the actual parameter, is passed to the function lambda v dot e by substituting the argument for the formal parameter v in the function. This is a formal parameter. In place of that, you are putting the actual parameter and evaluating this. So this is the actual function application or the actual substitution rule, which is the beta reduction. The catch being that the substitution has to be safe in terms of the rules that we have seen, that the variable you're substituting for must not be captured, must not be bound, and the variable that you result in the resultant expression should not get changed from free to bound. So if v is a variable, this is your beta reduction. Actually, between these two slides, the lower part has only changed. So the definition is just repeated for your ease. The left side of beta reduction is called a beta redex, derived from reduction expression, and the meaning an expression that can be beta reduced. A beta redex is something which can be beta reduced. The beta reduction is the main rule for evaluation in the lambda calculus, and alpha reduction makes the substitution for variables valid. We have already seen this in the examples. So the evaluation of a lambda expression consists of a series of beta reduction. So now you can see the process. You are given a lambda expression, you keep on doing beta reduction. That is, by every beta reduction, you are evaluating some function. You keep on doing that. If you get stuck that your substitution required for beta reduction is not remaining safe, you use alpha reduction to rename variables. So that it says that consists of a series of beta reduction, possibly interspersed with alpha reductions to change bound variables to avoid confusion. So when we write E is reduced to F, we mean E is beta reduced to F or E is alpha reduced to F. And in the same kind of notation that you had seen in the compiler, grammar reduction production rules, we use that same notation. So the reduction star is arbitrary number of applications of the reduction, and that operation is reflexive and has a transitive closure. Why is it reflexive? Because E can always be thought of reduced to E, the same expression, by zero application of the reduction. It's a same reduction. And for any three expressions, if I have a reduction from E1 to E2 and from E2 to E3, that implies that I have a reduction from E1 to E3. So that is a transitive closure. So that makes the chain of reductions possible, because without the transitiveness, you could not have had that. So the reflexivity gives you the starting point. It is the zero of the system, and transitivity gives you the way to go forward. And by whenever in this reduction, whenever you are doing an alpha reduction, you are just having renaming. But whenever you are doing a beta reduction, at least one function has got applied. So since the original lambda expression will have certain finite number of possible function applications, this process at some point will terminate when there will be no beta redux left to be reduced, and that expression will be taken as the semantics or meaning of the original expression. So the goal of evaluation in the lambda calculus is to reduce a lambda expression via these reductions until it contains no more beta reductions. To define an equality relation on lambda expression, we also allow a beta reduction rule to work backward. So if E is beta reduced to F, then F is actually equivalent of E. So you should also be able to come from F back to E. So that is called abstraction. So reversing the beta. So if you just going back, this is the beta reduction rule. So you have the function applying on E1 and expressed in terms of a safe reduction. So you can write it just the reverse way. So this substitution means that you have this function being applied onto E1. So you can go either from this to this or from right to left. So these two rules taken together. So you can see what we are trying to say. We are trying to say that one is getting transformed to the other. And that transformation is both ways. So in terms of a function application in C, it often is not both ways. Factorial 5 is 120, but given 120, you may not get factorial 5. There are several ways to get to 120. Right? But here, we are defining a process which is both ways convertible, which makes sure that always the two sides are equivalent. And the reduction and abstraction taken together is called beta conversion. So E and F are beta convertible if E is beta reducible to F, or F is beta abstractable to E. Then we say there, if any one of them happens, the other will always remain. Right? So this is naturally makes that this conversion process is both reflexive and has a transitive closure. So under such conditions, the two expressions will be called equivalent or equal if they have a beta conversion between them. It does not matter which expression I deal with, both have the same semantics. Right? Now, naturally, the application of this beta reduction or abstraction can happen in the same way of building up, that if E1 is convertible to E2, then if I apply E1 on some lambda expression E and E2 on some lambda expression E, then this application E1E is also convertible to E2E. That is, these two lambda expressions, if they are equivalent, then their application on a common lambda expression will also be equivalent. Similarly, if E1 is convertible to E2, then if I apply the same lambda expression on both of them, then the resulting expressions will be equivalent. That is, I take the same function and apply to E1 and E2 two parameters which are equivalent, then I'll get equivalent results. And it says if E1 is convertible to E2, then an abstraction built on E1 by X, an abstraction built on E2 by X. So if the two bodies are equivalent, then the function built on it using X as a parameter are also equivalent. These are just consequences of what we have seen so far. Right. So before I go forward further, let me just stop and ask if there are questions, if things. This alpha and beta reduction and this conversion process is the core of the simplification or semantic expression of any lambda expression, because again we have now, after defining the beta reduction, we have now satisfied both the requirements we started with. One is of the vehicular language, which is lambda itself now, because we are converting the expression into a resultant lambda expression. And when do we say that it is indeed the semantics of the original expression? When I reach an expression where there is no possible beta reduction, there is no possible function applications that are left. So kind of I reach a fixed point. And the whole transformation process is completely mathematical and sound and complete as well. So alpha and beta reductions together, or often we say that the beta conversion is a sound transformational process to make sure that given a lambda expression is, no matter who performs it or if the machine performs it, it will always get us the same lambda expression by equivalence, which is the meaning of the original lambda expression. Right? I do not see any questions, so let me go back. So the third rule is, as I said, that the function equality rule says that if a variable v, if v is a variable and e is a lambda expression which denotes a function, and v has no free occurrence in e, then lambda v dot e applied to v is same as e. That is, if you just try to see what is being said, there's I started saying that this is function equality. How is it? Because e is a function. E is a lambda expression denoting a function. Otherwise, eta reduction rule does not apply. If e is not a function, then it has no meaning. Now, what we are saying that if we take a variable v that is not free in e, right? Otherwise, it will get changed to bound. That's true. It has no free occurrence in e. Then, if I do an application of e on v, and on the resultant, if I do an abstraction on v, then what I get is the original function, which is understandable. So lambda x dot square x is same as the function square, or lambda x dot add 5x is just the currying add 5. It abbreviates to add 5, right? So this way, several functions by eta reduction can be shown to be equivalent and made simpler. Now, just to warn about the pitfall, V has no free occurrence in E. Just to understand that, let us see that I have lambda x add xx. So it's kind of a doubling function. I cannot reduce it to add x because left hand side is a doubling function and right hand side is a curried form of add function. Right. So this is happening because it is not free. The V that I'm applying to, this x that I'm applying to, is not free. It is already bound in this expression. Right? So keeping that in mind, I can always do a eta reduction and get equivalent functions where eta reduction justifies an extensional view of functions. This is called extensional view that I was just explaining a while ago. That is, two functions are equal if they produce the same values when given the same arguments. So for all x, if fx is equal to gx, then f is equal to g. Though their actual expressions may be different, the way they have been written may be different, but they are considered in the lambda notation to be the same function. So that leads you to the extensionality theorem, that if f1x reduction star is e and f2x reduction star is e, where x is not free in f1 or f2, then f1 and f2 are equivalent. Right? So if these two functions, f1 and f2, applied on the same variable produces the same result expression e, under the constraint, of course, that x is not free in f1 or in f2, because that will make the substitution, that may make the substitution invalid, then these two functions, f1 and f2, are equivalent. These are same functions. Right? So, and obviously it says that these reductions now include eta reductions. So this rule is not strictly necessary for reducing lambda expressions and has some problems when you do it under constraint, but you put it for the sake of completeness so that equivalent, all different equivalent functions do not turn out to be different lambda expressions. You can actually call them to be equivalent and take them to be different representations of the same function. Right? So finally, we have the delta reduction. Delta reduction is not there in the pure lambda calculus, where predefined constants are also not present. But usually, I mean, we are doing an kind of extended lambda calculus where predefined constants are allowed. So these are rules associated with the predefined values, and those are called delta rules. So delta rules come from the domain. Delta rules are not rules of lambda calculus. They are rules of the predefined constant domain that you are assuming. For example, add 3, 5 by delta rule is 8, or not true in Boolean by delta rule is false. So when we did this, we had this twice, and just showing an example of reduction, we did twice. So if we apply this twice on alpha lambda n dot add n1 5 f and x, This is the f, add n1, and this is the x, which is 5. Then by beta reduction, I will do this application often here, expanding. This is just expanding twice into the actual form. By beta reduction of f, I will put add in here. By beta reduction again, I do put in here. By beta reduction again and put in here, and finally get to this expression. This part, earlier part, we have seen before. All that we were just doing it intuitively. Now we are doing it through a very rigid, safe mathematical transformation process. And the final, we'll say the semantics of this expression, twice lambda n add n1 5, is this lambda expression, because there is nothing left to be done. But if we make use of the delta rules, then knowing that the rule of this constant, I know the rule of the constant says that add 5 1 is 6 and add 6 1 is 7. So I can apply delta rules to get to 7, which is even simpler. But if I if I'm in the pure domain and I do not have implicit semantics for them, so delta rule, what the delta rule is saying is something very, very similar to what we do in terms of compiler translation, that you translate it into an expression into a language which you already know. So it is still a lambda expression, but it is a lambda expression of just variables and names, constants, that's all. But you now are putting the meaning of the domain, that add 3 5 is 8 is not a lambda conclusion. It's come from the language of arithmetic, or that not true is false comes from the language of Boolean algebra. And you have reasons to believe that that language is mathematically sound, complete, and well understood. And you choose to use those semantics of the external language of predefined constants to reduce. So that is the reason delta rule is different from the rest three. So that gives you a even simpler lambda expression. But if you choose not to use this semantics of external language of addition of arithmetic here, then your final reduced lambda expression is this expression, which cannot be reduced any further. So that is the semantics of the original lambda expression. Right? So to conclude on the reduction process, what we have done is we have looked at the basic definition or built the rules of substitution, understood the issues of safety by either a bound variable being replaced or a free variable becoming bound by substitution. And we saw that these, if we make separate rules for checking this out and we create a renaming process, then we can have a sound and complete set of substitution rules. And based on those, we have defined alpha reduction for renaming, beta reduction for safe substitution, which we have also argued are basically, as it is reducible, in the reverse way, it is abstractable also. So we say they are beta conversion rules. And then we have looked into eta reduction to say under what condition two functions can be treated to be equivalent is if they produce identical result when applied on identical parameter every time. And alpha, beta, and eta rules form the foundation of lambda calculus semantics, and gives us for any given expression, it gives us the most reduced expression. And then we have talked about delta rules, which goes beyond the lambda calculus, which borrows semantics from the predefined constants domain that it is given to use, and based on the application of the semantics of that domain, delta reduction can reduce lambda expressions even further and give you a more concrete semantics, right? So that's let me stop here and ask check if we have any other question. I mean, we are kind of at the crux of the whole lambda calculus process. We have defined the syntax in a crisp manner in the last module, and now we have a way to define the semantics, with the beauty that the semantics of a lambda expression is in the lambda language itself. It is another lambda expression, but it is kind of a reduced one. So it's a reduced expression which is reduced up to function equality and application of domain semantics if used. So with these two, we kind of get a complete lambda language to work with. So I'd just like to see if there is, I hope on winter morning people are not sleeping off after logging in. Anyway. I need to share. Okay. Okay. Now, let me just introduce that. So we have seen how to do these reductions and how to get to the reduced expression. Now, often in an expression, there are multiple choices of which substitution we do in what order and in what way. So we talk about the evaluation strategies for function evaluation, function call. So before we get to that in the lambda domain, I just wanted to quickly recap the fact that we do have the examples of several different evaluation strategies in normal programming languages, and it's good to be conscious about them all the time. For example, the most commonly known is call by value in C or C++, where the argument expression is evaluated and the resulting value is bound to the corresponding variable in the function, the former function, frequently by copying the value into a new memory region. So we all know this. This was foundational for C and also available in C++. Then you have call by reference. A function receives an implicit reference to a variable which is used as an argument, which is, we say, is the alias of the reference, and rather than a copy of its value. So CBR may be simulated also in languages by call by value. The classical example is trying to write a swap function in C, where using call by value, you cannot actually have the result of swap because the swapped values do not come back to the actual parameter. So we do an indirect addressing and make use of that by pointer, and often that is known as call by address. So that is another mechanism. That trick that we use in swap by using a pointer to get an effect of an output parameter under the case of call by value. I've heard some people refer it as call by reference. Please do not do that, because these are completely different mechanism. Because call by reference uses just a different name for the variable, and call by address uses a reference, uses a pointer to that variable. So these are completely different things, but these are the different evaluation strategies you have. I think I mean I'm trying to give you a correlation between the fact that when you have evaluation requirement of an expression, then how you do that evaluation may also eventually affect the result. So that ramification is what we are trying to see. Then you have another mechanism which is called CBCR, call by copy restore, which was there in old Fortran, a special case of call by reference where the reference is unique to the caller. That is, you kind of copy the variable when you call and copy it back when you return. So it's called copy in, copy out. That was another mechanism. There's a call by name, which is the macros in C++, where your macro parameter is substituted textually in the macro body by the variable that you use to call the macro. So they are substituted directly into the function body, but no evaluation is done. The evaluation is lazy. The evaluation will happen when that function will go into execution. That macro will go into execution. But the actual call and the disappearance of the macro happens by name, by substitution of the variable. And there are certain other variants like call by need, which is a memorized variant of call by name, where if function argument is evaluated, the value is stored for subsequent use. So those kind of. So there are different strategies that programming languages have used to kind of express functions and their evaluation. So you can very easily, I mean, even if we do not go to old mechanisms like call by copy restore of Fortran or value result of Fortran, or if we ignore macros for now, which is done by the CPP. But even between call by value and call by reference, you can see that the way, if depending on whether you have made a reference parameter or you have made a value parameter or you have made an address parameter, call by address parameter, depending on that, the behavior of swap could be different. And so the function remains the same, but the way you evaluate will also make differences in terms of the result that you get. Right. So this is a example. That's just in case you are interested to actually go to the low level and see the result. So coming back to the Lambda domain, we want to build sound. We have built sound reduction rules. Now we want to build sound reduction strategies. So we say that a Lambda expression is in normal form if it contains no beta reducts and no delta rules if in applied Lambda calculus. Then it is said to be a normal form, that there is nothing more that you can do. So just to get back to that example before, here, all these Lambda expressions you have are not in normal form, except this last one. And if you are using beta reduction, if you are using beta rules, then this 2 is not in normal form, only 7 is in normal form. But there are no reductions possible. But if you are in the pure Lambda calculus, then this is your normal form, because there is no more beta reduction that you can do here. Right? An expression in normal form has no more function applications to evaluate. That's the basic question. So if we have this, then there will be certain obvious questions that will come up. Can every lambda expression be reduced to normal form? Naturally, that's a big question, because otherwise this cannot be a general strategy for expressing semantics. Is there more than one way to reduce a particular lambda expression? We have shown that reduction can be done. We have shown that the reduction will be sound. But is it possible to reduce in more than one way? Now, if the answer to the question at 2 is correct, is yes, if there is more than one reduction strategy, will each one lead to the same normal form expression? Or will it matter as to what way I have reduced? That if there are multiple ways to reduce, will these different reductions lead to the same expression? Finally, is there a reduction strategy that will guarantee that always a normal form expression will be produced? So these are some of the questions before we write off saying that we have a complete beta reduction strategy to complete reduction mechanism to work with. Now, we try to answer them through some examples. So can every lambda expression be reduced to a normal form? The answer is no. I think you can recall what this is. This is SA, right? Self-application. So this lambda expression. So you are doing this. So you will obviously, to apply, you will do some renaming and all that. But after that, it basically comes back to the same expression. And your basic requirement of having a normal form is that there is no function application left, but no matter how long you keep on applying, the function application will remain possible in this expression, right? So we are in a little bit of soup, because it may be that I have a lambda expression which does not have a normal form. That means which in my way does not have a semantics. Second question, is there more than one way to reduce a particular lambda expression? Yes. Take a lambda expression, and this is one reduction. I have done it. This is called the outermost. I'm coming from out to in. So substituting 7 for x, getting this, substituting 5 for y, getting this, then getting into the inner expression. Finally, coming to the normal form, delta rules result. Here I'm doing the same thing, but here I was doing from external expression to in, outermost. Here I'm coming from inside to outside. So I'm first doing this. So lambda z mul xz is applied onto 3. So I get mul x3. And I keep on doing from inside to outside. I get to same normal form as in here. And after delta gives me the same 26. I can do mixed. I first did in, then I did out, then I did in, get to the same one, right? So to answer the question, is there more than one way to reduce a particular lambda expression? The answer is yes. There are multiple ways to reduce an expression. The third, since we have seen that there are multiple ways, the question is there more than one reduction strategy? We know there is. Will each one lead to the same normal form expression? Consider this. Now, one could be that this whole I'm applying this function onto this lambda expression, which is SA we know. So if I apply from outside, then I'll apply it here. I'll substitute this whole thing for y and evaluate for 5, which is 5, because y has no instance here. If I do inside out, then I'll first apply this. And we have already seen if I apply this, I get back this. So I'll continue. So it is possible that some reduction strategy will lead to a normal form and some will not. Right? We are getting into, sticky water. So the final question, is there a reduction strategy that will guarantee that a normal form expression will be produced? And there is a foundational result by Curry, who proved that if an expression has a normal form, because we know the expressions may not have normal form, like I say, if an expression has a normal form, then it can be found by leftmost reduction. If I do a leftmost reduction, then if there is a normal form, I'll get that. So a normal order can have either of the following outcomes, that it reaches a unique, in the sense up to alpha conversion, normal form lambda expression, or it never terminates, as in the case of SA. Now, unfortunately, this decision problem, this problem is undecidable. That there is no algorithmic way to determine for an arbitrary lambda expression which of these outcomes will occur. So you can correlate this to the halting problem of Turing machine, that it given the Turing machine and the input, it is not possible to build a Turing machine which will say whether the given Turing machine will halt on the given input. So it can be mapped to exactly that foundational problem, and it's undecidable. So there are possible sticky waters that will happen, that would exist, where a lambda expression does not have a normal form, where there are different ways to get to the normal form, and the basic fact that we do not know whether a lambda expression will have a normal form. But if it has, then it can be uniquely found by leftmost reduction. Right? So that is the basic result by Church. I think there are only 10 minutes left. I think it will be better to do it in the next class, because I do not want to break in between normal and applicative order. So just give you the basic insight into the reduction strategy, that is how the order of evaluation might impact the whole process. Okay, so let me stop here, and if there are any final questions, let me take that. Or and I'll give this presentation to the TS for upload on Moodle, so you'll be able to refer to that. But it is high time, and your first assignment will also get Srijani, has the first assignment been published, or it'll be done today?
No, sir.
Okay.
Today, then I'll release.
So we'll release the first assignment also today, and which is not including semantics. It's based on the syntax part of it. And this presentation will also be uploaded. So it's time that you start practicing well, because these two modules are kind of foundational. If you have understood the language of Lambda, how to write expressions and what do they mean by reduction, if you have understood these two basic processes, basic stuff, then everything that will follow will be kind of decorative on this. kind of adding type on this, extending the language, Lambda language with different other builder mechanisms, or kind of using it for expressing semantics of constructs that we are more commonly conversant with. All these will become quite simple and easy to understand and kind of natural, I would say. I mean, well, there are some trick points, but in most cases, once you understand the syntax and semantics of Lambda language really well, which needs just a little bit of effort, maybe you'll need 2 days to get there, but some serious thoughts you have to put in, then it becomes much easier to handle the rest of the course. And we will soon introduce uh, pure functional programming languages for your practice and fun. I mean, I know doing hardcore theory all the time may not be very digestible for everyone, and it's also, we are engineers, so we have to practice in terms of those languages. So we'll soon introduce those languages as well. So since there are no more questions, let me stop here today. Thank you all very much, and have a very nice day.